I'm Anil Kumar, and in this video, we'll understand the very basic concept of solving differential equations. In coming videos, we'll take up many examples based on different types of differential equations. But here, we'll start with the very basics. That is, we get differential equations from differentiating some functions, correct? So if I am finding the solution of a differential equation, we are trying to get the function. That's the whole idea. So it's kind of going reverse, right? So solve differential equation means what? Let's first understand that, and then we'll come to the point. So when we say solve differential equation, what do you expect as your solution? It really means we are looking for the function, right? This is the main thing which you should understand. Whenever we say solve a differential equation, we are looking for the function, right, whose derivative is known to us, right? So we are doing the reverse thing, and this reverse thing gives you an idea of antiderivative, right? So that's the concept. So I hope you understand why we have taken up this video. It is to solve differential equation using antiderivatives. And this is really very important concept, since in many practical situations we know the rate of change. We know the rate of change. The thing is, we know rate of change, and we want to find the function. So for example, we know that let's take some example as growth of bacteria, right? Let's say growth of bacteria. So let's say we have a species and we know how the population is changing. That means we know the change in population, right? Growth rate. Let's say growth rate is known to us, and what are we interested? Number of bacteria at some time, right? So, or after some time. So that is what we are interested in finding. So we know the rate of change. That means we know the growth rate of bacteria. We know they multiply so that every day they become twice the number or 4 times the number. But we want to know how many of these will be there after a week. Now that is what we're talking about. So since we know the rate of change and we want to find the actual number, in that case, we are finding antiderivative. So we are doing the reverse thing, right? At times, you'll also see that like in a car you're going, and let's say you can read your speed. So we know the speed, that is velocity, which is actually rate of change of displacement, right? So we know the rate of change of displacement. We know rate of change of displacement. But we want to know how much distance are we going to cover. We want to know how much distance are we going to cover, let's say in an hour. Now that becomes easy if this rate of change is constant. But if the speed is changing, let's say sometimes we drive at 80 kilometers per hour, sometimes at 90, sometimes at 100. And if you take few readings within a span of, let's say, 5 minutes, and you need to get an idea how much distance will you cover with that kind of driving, that's the question which I'm talking about. So you could find that the distance covered is s. That means we want to find s. Do you see that? So from known rate of change, we want to find the function, right? From known rate of change here, we want to find the population in this case, right? We want to find population P, right? Now this population may be a number, but this could also be a function, since the velocity, as I said, could be varying, right? So if I have, let's say, if I see a pattern in which the velocity is varying, I could have a table of values. From there, what is going to be the distance covered during that time could be calculated. And that kind of reverse thing is what we're talking about now, right? So this is what we're talking about. So these things could be calculated using antiderivatives. To give you an idea how could we really solve such a question? Let me take the first example, which is dp/dt. So we know that the population of bacteria is actually proportional to the number of bacteria it is, right? So I have small space here in which we can work. So let me change the ink and explore this particular concept. So let's say what we know is that the rate of change of bacteria is basically proportional to the population of bacteria at any time. So this could be written as that rate of change of bacteria is equals to some constant times the population. Correct. So that becomes a differential equation. We have rate of change on one side. It's a first order differential equation. And we need to find what is going to be the population after some time. Right? So in this particular case, we're trying to find the function p when we know its derivative. Right? So here we want to find function p when derivative is known. So that is done by antiderivatives. Right? And in this particular case, what we are saying here is that rate of change is same, but a constant times the function itself. And we are aware from our knowledge about derivatives that the function which can do this is kind of exponential function. Is that okay? So we can say c e to the power of something, let's call this kt. That could be the function whose derivative is going to be a constant times the function itself, right? So dp/dt is equal to what? Is equals to c times, let me write this as k, right? K, derivative of this is a constant, e to the power of kt. Do you see that? Now c into k, both are constants, right? C into k, both are constants, so we could write this as some other constant k, e to the power of kt. Do you see that? Now if you compare these two equations, we know that our function is this function. Do you see that? So, right? So, I mean, from here, let me rechange this kt, or specifically, I could write this as k times c e to the power of kt, right? Since we started with that function, right? So what we see here is that knowing the rate of change, we can find the function for find the equation of the original function, as we've done here, right? So in this case, we can see that derivative of this function is what we need. Antiderivative gives you what we want to know, right? So that's the concept of antiderivative. And so from here we can say, well, the population should be c times e to the power of kt if you compare this with this equation. Is that okay? So we have a constant, right? We have a constant and p, and in this case, if I rearrange it, it becomes c, where c is the initial value of the population of the bacteria, right? So this small example actually gives you an idea of how to link derivatives and antiderivatives to solve real life solutions. So in this particular video, what we learned is that in cases where the rate of change is known to us and we want to find the function, we can use antiderivatives to find the function. So it's kind of a backward calculation as we've done for differentiation, right? So knowing derivatives of a function helps to find solution to such real life situations using antiderivatives. So we'll take a few more examples, and I hope this concept is clear. Mainly, whenever we are solving differential equations using antiderivatives, we're trying to find a function, and this function could be seen from our knowledge of derivatives, right? So it's like backward calculation, right? So that's how we're going to solve few questions in this video, in this list of videos. I'm Anil Kumar, and I hope that helps. Thank you, and all the best.